Okay, so let's take a look at the first problem I got incorrect. What is the conversion factor between centimeters squared and meters squared? So my first choice of answer was A. Now this is incorrect because I did not actually pay attention to the units, and instead of converting from centimeters squared to meters squared, I actually went from centimeters alone to meters. So this is incorrect. So how do we actually find the answer? Well, first let's start off with how many centimeters are in 1 meter. We know that 100 centimeters go to 1 meter, so how are we going to go from centimeters to centimeters squared per 1 meter squared? Well, in order to get squared units, we find the area of a shape. Let's say each side of this shape is 1 meter or 100 centimeters. So what do we do now? We find the area of the shape. So you simply take your area, which is equal to the base times height, which would be 100 centimeters squared. If we were to apply this square to each term, you get 100 squared, square the units, and you get centimeters squared. Now this is perfect because we have what we're looking for, centimeters squared. So now let's jump back to where we originally were and say that if we had 100 squared centimeters squared, we would have 1 meter squared. How did we already get our 1 meter squared? Well, if we were to, you see over here, all we had to do was square our original value. So what's stopping us from squaring 1 meter squared? So if we said 1 meter squared, you apply it to each term to get 1 meter squared. So now all we have to do is break this up. So let's break it up into multiples of 10. 100 squared becomes 10 to the 4th centimeters squared for every 1 meter squared. Now let's divide 1 meter squared by 10 to the 4th centimeters squared. So we can convert it to 0.0001 meters squared for every centimeter squared. So as you can see, this matches up with choice B, which is the correct answer. And this concludes problem number 2. Okay, our next question is, the density of a solid is defined as the ratio of the mass of the object to its volume. The dimension of density is, my first choice was A. Now this is incorrect because, well, my mistake was misunderstanding the meaning of each letter we have here. So after some tutoring, I realized that M actually means mass, L is length, and T is time. And as the problem states, to find density, it is defined as the ratio of the mass to its volume. So we already know A is incorrect because, well, if L is equal to length, we don't divide our mass by our length. So how do we find the right answer? Well, taking from this, since we know that D is equal to M over V, we have our mass over volume. But so in density, we don't need time. Let's forget about that. We have our mass, which we started with. That's perfect. So all we have left is length. How do we get volume from length? Well, let's visualize it. Let's say we have a cube or a box. And we have our length of each side of said box. Well, how do you find the volume from the 3 different lengths? Well, if you remember length times width times height, you can easily say that to find the volume of this cube, we simply have to multiply length times length times length, or length cubed. So now this is perfect. We have either B or C with the answer length cubed. So how do we determine which is which one is the correct answer? Well, if we take a look at this, m over v, or mass over volume, we have to have our length cubed at the bottom, but this isn't a choice. So how do we change the form of this to coincide with one of these answers? Well, if we were simply to move our length cubed to the numerator, we can say mass times length, and our cube will become negative because it is moved to the numerator. So this is perfect. Now we have C. So C would have to be the correct answer. And that concludes problem number 3. Okay, our next problem is problem number 4. The position x of an object is given by the equation x is equal to a plus b times t plus c times t squared, where t refers to time. What are the dimensions of a, b, and c? So what I did was that I wrote down a, b, and c, and I set them all equal to L, or length. So we know that x is already equaling position, so we don't need to worry about that. If a were to equal L, that would just be written in meters, because L is distance, and distance is usually in meters. Now what I did here was that I multiplied b times time, or t, because that is shown in the equation above. So if we were to isolate b and divide each side by t, we would get b is equal to length over time. So that would be meters over time, or seconds, meters per second. And then you do the same thing for c times t squared to give you your distance over time squared. So if we were to take all of this and plug it into the equation, x, or distance, L, is equal to a meters, because that's only in distance, plus b meters per second here, and then c meters per second squared. And here we also know that b and c are being multiplied by t and t squared. So b times t and c times t squared. So what does this tell us? Well, if we look over here, t and s both mean time, because s means seconds. So we know that t and s can be canceled out at b, and t squared and s squared can also be canceled out. So now we're left with a meters, b meters, and c meters, also meaning these are all equal to distance. Meaning that instead of c, which I chose first, it's actually a, distance, distance, and distance. And that concludes number 4. All right, number 5. Car A is traveling at twice the speed of car B. They both hit the brakes at the same time and undergo identical decelerations. How does the distance required for car A compare with that for car B? So we know that the velocity for car A is twice the velocity for car B, so we set them equal. We know their accelerations are both identical, so we set them equal as well. We also know that their final velocity would be 0 because they are decelerating and will eventually come to a stop. And since we have our final and initial velocity, we would have our change in x of A and change of x in B. Knowing this, we are able to use this equation right here. So now that we have our equations written down, we know that our velocities are both equal to 0, as shown up here, meaning that we can move this portion for B to the other side, giving us our initial velocity of B, car B, is equal to negative 2AB times the change in XB. So since we have our initial velocity for car B, that means we can plug it in for our initial velocity of car A. So let's do that. So we can say 2 times our initial velocity for car B, because, again, our velocity for car A is twice the speed. So now from here, we just simply do the math. So now I've narrowed it down to -4 times the change of x in B and the change of x of A. So all we have to do is switch one of them to the other side to show us that the distance required for car A to stop will be 4 times the distance required for car B. And that is our answer. Okay, number 6. The slope of a line connecting 2 points on a position versus time graph gives, and we have a set of options. My first choice was B, which is incorrect. I don't know why I chose B, but I did. So to find the right answer, first we have to look at our graph, which I drew here. We have x on our y-axis and t on our x-axis, or position versus time. So how do you find the slope? Let's look at that first. Well, you say m is equal to the change in y over change in x, or in this case, change in x on the y-axis and the change of t on the x-axis, which will give you x sub 2 minus x sub 1, because that's what we do to find the slope, and t sub 2 minus t sub 1, or 1, my bad. So what formula is this? Well, we know that when we use this formula, we're solving for average velocity. So the correct answer would be C. Okay, number 7. The motion of a particle is described in the velocity versus time graph shown in the figure below. We can say that its speed. So my original answer remains constant, which is incorrect, because I did not know how to read this graph. Well, actually, how you read it is that, well, we have our negative values below 0, obviously, and our positive values above. So it starts from below 0, and just because it's moving in a straight line at a constant rate, that does not mean it remains constant. Actually, since we're starting from our negative values, it shows that, let's say we have a car. Actually, this car is accelerating, and I say accelerating because we have velocity versus time, so it's accelerating backwards. But then after some time, it comes to a stop because it reaches 0. So that means it stops. And then over here, it continues upwards towards the positive values, meaning that after it has accelerated backwards, it does that but forwards, meaning that first it would, or the velocity or speed decreases and then increases. So the answer would be D. 8. The position of a particle as a function of time is given by x of t is equal to 3.5 meters per second times time minus 5 meters per second squared times time squared. What is the average velocity of the particle between t is equal to 0.3 seconds and t is equal to 0.4 seconds? So we know that t1 or time 1 would be 0.3 seconds and time 2 would be 0.4 seconds. We were also given this formula up here, so let's write that down too. So 3.5 meters per second times t minus 5 meters per second squared times time squared. So what we can do to find x, in order to find our average velocity, we can plug in our time values. So let's do that. Okay, so now we plugged in our time values for the equation 2 times for time 1 and time 2. And now we know that x1, after plugging in time 1, we have 0.6 meters. For x2, we have 1.24 meters. So this gives us our displacement, and we'll plug that into our next equation. So since our problem is asking us for average velocity, we know that we have to have average velocity is equal to x sub 2 minus x sub 1 t sub 2 over t sub 2, minus t sub 1, which in turn would mean that we plug in the values we found and the values we were given to give us 1.24 meters minus 0.6 meters over 0.4 seconds minus 0.3 seconds. This will give us an average velocity of 0.4 meters per second. And that is our answer. Number 9. At the instant a traffic light turns green, a car that has been waiting at the intersection starts ahead with a constant acceleration of 2 meters per second. At that moment, a truck traveling with a constant velocity of 15 meters per second overtakes and passes the car. Calculate the time necessary for the car to reach the truck for part A of this problem. So let's separate what we know into columns. So we have our car and our truck. We know that our car has a constant acceleration of 2 meters per second, and our truck has a constant velocity of 15 meters per second. Now we know that since it's going at a constant velocity, there will be no acceleration, meaning the acceleration is 0. And since our car had been stopped at a traffic light, we know that its initial velocity would be 0. Now in order to find our time, we can use this equation right here. So for the car, we have our car, we can plug in this information into this equation. So we know that x would be equal to, so our initial velocity would just be 0. So now we have 1/2 of a times t squared. Now for our truck, we would do the same thing, saying x is equal to, or let's say x1 and x2. X sub 2 would be equal to, our acceleration here would actually be 0, meaning this entire thing would be 0 for x sub 2. So we would be left with velocity times time. Okay, so if we were to put this in a graph, we know that our truck is moving at a constant velocity, and our car is accelerating. And at some point, they will pass each other and reach the same point on the graph. So this tells us that we can set these two values equal to each other. So now we have 1/2 times acceleration times squared is equal to our velocity times t, or times time. Okay, so I did the math, and all I had to do at the end was plug in what we have here into what was left. So we have 2 times our initial velocity, or the truck's velocity, so 15 meters per second, divided by our acceleration, or 2 meters per second. So now all we have to do is solve for that, and we get 15 seconds. And that is our answer for part A. Okay, so now we have part B. So they want us to calculate the distance beyond the traffic light that the car will pass the truck. So all we have to do for this one is plug in the information we already know. So we know that our velocity of our truck is 15 meters per second, and multiply that by our time, which we found to be also 15. And that will give us 225 meters. And since these two were set equal to each other, then if we were to plug this into this equation, then we would get the same answer. So our distance is 225 meters. And that concludes part B. Finally, part C wants us to determine the speed of the car when it passes the truck. So, since we solved for everything else, we can use the formula velocity is equal to initial velocity plus acceleration times time. If we were to plug that in, we would have our initial velocity as 0 plus our acceleration of 2 meters per second squared times 15 seconds, which would give us a velocity of 30 meters per second. And that is our answer. So number 11, A graph of position as a function of time is shown in the figure below. During which time interval could the object be possibly moving with non-zero constant acceleration? So my first answer was C, which is incorrect because I had misread the axes. Well, what is this measuring? We have displacement versus time. That would give us velocity, but what this is asking for is a non-zero constant acceleration. So if we were to graph acceleration on a velocity graph, it would be exponential because the velocity or speed is always increasing or decreasing. So it would look like a curve. So therefore, the correct answer would be D, from 6.1 seconds to 7.9 seconds. So within this interval. And that is the answer for number 11. Number 12. Two objects are dropped from a bridge an interval of 1 second apart. During the time that both objects continue to fall, their separation. Now my previous answer was C, which is incorrect. Now, the best way to find this is to visualize this on a graph. So we know that when you drop something, it accelerates at 9.8 meters per second squared. So the first object, say object 1, it's accelerating. But then the next object, object 2, is dropped a second later, and that's accelerating. Now what do we see here? We see that, yeah, they're close together once they're dropped, but they slowly start increasing as time moves forward. So therefore, the correct answer would actually be increases. So the separation increases. 13. A rock is dropped from a vertical cliff. The rock takes 3 seconds to reach the ground below the cliff. A second rock is thrown vertically from the cliff. It takes 2 seconds to reach the ground below the cliff from the time it was released. With what velocity was the second rock released? So that's what we're looking for, the velocity of our second rock. Well, let's write down what we do know. We do know that rock 1 took 3 seconds to reach the ground. So we know that rock 2 took 2 seconds. We know that since rock 1 was simply dropped, it had an initial velocity of 0 meters per second. And since we're dealing with free fall, that means both of them would have an acceleration of negative 9.8 meters per second squared. And since we don't have our since we don't have our final velocity, then we're not going to be able to find that. So what we can do is look for our change in x, or in this case, change of y, since we're dealing with a vertical. So we're trying to look for this. So how do we do that? So to solve for our change in y, we can use the formula change in x, or in this case change of y, is equal to the velocity times time plus 1/2 of acceleration times time squared. And since we only have 2 values that we know for our second rock, we were not able to plug this in, but we can do that for our third rock because their change in y would both be the same since they are thrown off the same cliff. So let's do that. Okay, so now that we have our values for rock 1 plugged into this formula, we are able to get negative 44.1 meters. And the reason it's negative is because we're moving backwards towards the ground from the top of the cliff. So now we know our change in y. So since we have 3 values for rock 2, now we're able to solve for its initial velocity. So let's plug in what we found, which is negative 44.1 meters, and then initial velocity times time, which is 2 seconds, 1/2 of negative 9.8. because that's our acceleration, times time squared. So now we just solve for it. After doing the math, we know that our initial velocity for rock 2 would be negative 12.25 meters per second. Or if you want to round that up to the right amount of significant figures, we have negative 12.3 meters per second. And this negative is indicating that it is going at this velocity downwards. And that is our answer. 14. Refer to the figure below. The components of vectors are... Now my first choice was A, which is incorrect. Now, how are we going to be able to find the answer? Well, first we have to know what our sine and cosine angles are. So sine 90 degrees is 1, sine 0 degrees is 0, cosine 90 degrees is 0, and cosine 0 degrees is 1. So what does this tell us? So first let's take a look at our A vector. We know that our AY would be 0, but our AX would have to be some value, and that would most likely be 1. So what this tells us is that we either have to have this angle at sine 90 degrees or cosine 0 degrees. So we know that D and E will automatically be eliminated because this conflicts with what we require. So now we take a look at vector B. Well, we know that we have an angle of 30 degrees, so that can be transformed into a triangle, or a 30, 60, 90 degree triangle. And what this tells us is that we can either take the sine or cosine of 30 degrees or 60 degrees in order to find our x or y values. However, what we already know is that our B vector is going in a negative direction in quadrant 2, and the only option with a negative bx value is C. So the answer would be C. And that concludes 14 and our final problem for this video.